Hello students, welcome to aimsindia online classes. This is a chemistry session. Here we are discussing about the chapter chemical bonding. In this session we are going to say about bond polarity, means polarity of bonding. Let us say about this in this session. The existence of an 100% ionic or 100% covalent bond represents an ideal situation. Actually, in reality, no bond or a compound is either completely covalent or ionic. There will be slight change in that. It won't be completely either ionic or covalent. The existence of this 100% ionic or covalent bonding is a purely ideal situation. But in reality, no bond or no compound is either completely ionic or completely covalent. Even in case of a covalent bond between two hydrogen atoms, there is some ionic character. So there will be slight ionic character even if you consider this as a pure covalent. When covalent bond is formed between two similar atoms, for example, in case of a hydrogen molecule H2, O2, Cl2, N2 or F2, in such kind of molecules which are formed with the similar atoms, the shared pair of electrons is equally attracted by both the atoms, isn't it? As a result, electron pair is situated exactly between the two identical nuclei. The bond so formed is called nonpolar covalent bond. Another way, contrary to this, in case of a heteronuclear molecule like HF, which we call as hydrogen fluoride, the shared electron pair between the two atoms gets displaced more towards fluorine, since the electronegativity of fluorine is far greater than that of hydrogen. The resultant covalent bond so formed is called as polar covalent bond. Okay. Now let us see in detail about these polar and non-polar covalent bonds. First let us say about non-polar covalent bond. The covalent bond formed between two similar atoms, that means atoms of same element or atoms with the same electronegativity, is known as non-polar covalent bond. What is it? The covalent bond formed between similar atoms or atoms with the same electronegativity is called non-polar covalent bond. It also can be defined as the covalent bond in which bond pair of electrons is equally shared between two atoms. Then the covalent bond so formed is called non-polar covalent bond. So in the non-polar covalent bond formation, the electron pair in which one electron is contributed from each atom, that electron pair will be equally shared by both the atoms. So this electron pair will be equally shared by both the atoms, hence that the resultant covalent bond is called non-polar covalent bond. For example, in the homoatomic molecules, homoatomic in the sense the molecule made up of same kind of atoms. In the homoatomic molecules like H2, O2, Cl2, N2, F2, etc. Let us consider H2 itself. The shared pair of electrons is equally attracted by both the atoms because both are hydrogen atoms, both are contributing one electron for sharing, and this electron pair is shared by both the atoms. And here, as both are hydrogen atoms, both will be having same electronegativity. What does it mean by electronegativity? The tendency of pulling the electron pair towards it. So this will be equal for both the hydrogen atoms. Thus, the electron pair is equally shared by both the atoms. The bond so formed is called as non-polar covalent bond. Okay. The covalent bond in which electron pair is equally shared between the atoms is called as non-polar covalent bond. Let us see now another kind of covalent bonding, that is polar covalent bond. The covalent bond formed between two dissimilar atoms, in the sense atoms of two different elements or atoms with different electronegativities, is known as polar covalent bond. It also can be defined as the covalent bond in which the shared pair of electrons is unequally shared. The bonded pair of electrons is unequally shared between two atoms is known as polar covalent bond. For example, if you see here, these two are considered as two atoms. Each atom is contributing one electron for pair sharing. Now, these pair of electrons actually should be shared with both the atoms equally. But instead of that, one of the atom is pulling those pair of electrons towards it. By that, electron pair is unequally shared between these two atoms. Such kind of covalent bond, which is formed by the sharing of bonded pair of electrons unequally between the atoms, is known as polar covalent bond. Let us see an example for this also. For example, in heteroatomic molecules. Heteroatomic molecules means molecules which are made up of different atoms or atoms of different elements like HCl, HF, H2O, NH3, etc. Let us consider HCl itself. The shared pair of electrons between the hydrogen and chlorine, instead of being shared equally, this electron pair is pulled towards more electronegative atom chlorine instead of being shared equally. So here in this bond formation, chlorine and hydrogen both are contributing one electron. But instead of sharing this pair of electrons equally, the pair of electrons are pulled towards chlorine more because of high electronegativity of chlorine. So here sharing is happening, but it is happening unequally, isn't it? So such kind of covalent bond in which electron pair is not equally shared is called polar covalent bond. In this, the shared pair of electrons will be pulled towards one of those two bonding atoms, which is having greater electronegativity, that pulls the pair of electrons towards it. Such kind of bonding is called, that resultant covalent bond becomes polar covalent bond. Okay. As a result of this polarization, means polarization in the sense the moment of pair of electrons towards one of the atoms. What happens then? One of the atoms, it gets slightly negative charge, the other one gets slightly positive charge because of the moment of pair of electrons towards one of the atoms. Now, the molecules possess, because of this polarization, the molecules possess the dipole moment, which can be defined as the product of the magnitude of charge and the distance between the centers of positive and negative charges. Okay, the dipole moment is defined as the product of the magnitude of the charge and the distance between the centers of positive and negative dipoles or negative charges. It is usually designed by a Greek letter nu. Mathematically, it is expressed as follows, like this: dipole moment mu is equal to charge into distance of separation. That means the distance between the centers of positive and negative charges. So the charge difference into difference of separation. This gives the dipole moment of that bonding. Okay, dipole moment is usually expressed in debye units. So for the dipole moment, units are debye units. Of course, it can be converted into Coulomb meters by taking this unit conversion. The conversion factor 1 debye is equal to 3.33564 into 10 to the power of minus 30 Coulomb meter. Here this is C representing Coulomb and M representing meter. So here by this polarity creation in the molecule in the covalent bond. Polarity in the sense what we told, when two dissimilar atoms participate in the covalent bond formation by sharing a pair, that shared pair of electrons are unequally shared between the two atoms. One of the atoms attract the pair of electrons towards it much greater than the other one. So this results in the polarization in the bond. So this polarization creates dipole moment. Okay. Further, dipole moment is a vector quantity, means it is directional, means this dipole moment will be from one charged particle to another charged particle, and by convention it is depicted by a small arrow with tail on negative center and head pointing towards the positive center. But in chemistry, the presence of dipole moment is represented by the crossed arrow. So this is a crossed arrow. Here it is there cross and it is arrowhead. Put on Lewis structure of the molecule. So the dipole moment in the bonding can be represented with this crossed arrow with the Lewis dot structures of those molecules. The cross is on positive end and arrowheads on the negative end. For example, the dipole moment of HF, hydrogen fluoride molecule, may be represented as this. We know in the hydrogen fluoride molecule, hydrogen and fluorine both are contributing one electron, and the pair of electrons are shared by both the atoms hydrogen and fluorine. But here fluorine is being more electronegative. It pulls the electron pair towards it, isn't it? As hydrogen is less electronegative than fluorine, it loses its electron towards fluorine. Because of that, hydrogen gets slightly positive charge and fluorine gets slightly negative charge. The slight charge formation is called here dipole, and this is because of dipole moment of pair of electrons towards one of the two participating atoms is called dipole moment. This dipole moment is represented with this crossed arrow. Here the head of the arrow is towards the negative end of the dipole, and the cross is towards the positive end of the dipole. In this way, dipole moment in a covalent bond is represented, okay, by using this crossed arrow. This arrow symbolizes the direction of the shift of electron density in the molecule. So that arrow, crossed arrow, representing the direction of the shifting of the electron pair or the electron density in the molecule. We have to note that the direction of crossed arrow is opposite to the conventional direction of the dipole moment vector. In case of polyatomic molecules, the dipole moment not only depend upon the individual dipole moments of the bonds, which are known as bond dipoles. Okay, this dipole moment not only depending upon the individual dipole moments of the bonds, which we call as bond dipoles, but also on the spatial arrangement of various bonds in that molecule. So the total, which we can say the net dipole moment of the molecule, depends upon both individual dipole moments of the bonds as well as the spatial arrangement of various bonds in the molecule. On these two, the dipole moment of a polyatomic molecule depends. In such case, the dipole moment of a molecule is the vector sum of the dipole moment of various bonds. So in these polyatomic molecules, the net dipole moment of the molecule is considered as the vector sum of the dipole moments of various bonds present in that molecule. Let us see some examples here. For example, in water molecule, which has a bent structure, there are two OH bonds are oriented at an angle of 104 degrees, 104.5 degrees, isn't it? These are water molecule. The net dipole moment of 6.17 into 10 to the power of minus 30 Coulomb meter is the resultant of the dipole moment of two OH bonds. So here the net dipole moment of this molecule is considered as this, because if you consider one bond in this molecule, that is OH bond, hydrogen is electropositive, oxygen is electronegative. So the pair of electrons shared here will be moved towards oxygen. That is represented like this, crossed arrow. The head representing the moment of electron clouds towards oxygen. In the similar way, in this bond also. So the moment of pair of electrons is in this direction. Here it is in this direction. Here it is in this direction. So that's why, as these are having directional property, these can be considered as vectors. Dipole moment as a vector quantity. Now for the overall molecule, the dipole moment for this water molecule can be considered as this. So here particular for this bond it is in this direction, and for this bond it is in this direction. The net dipole moment of this molecule, which we call as resultant dipole moment of this water molecule, will be in this direction. Okay, let us see some more molecules. The dipole moment in case of beryllium difluoride BeF2 is 0. This is because the two equal bond dipoles point in opposite directions and cancel the effect of each other. If you see, in the beryllium difluoride molecule, fluorine and beryllium both are forming a covalent bond by sharing a pair of electrons. But out of these two, fluorine is being more electronegative. So it pulls the pair of electrons towards it. By that it will get negative charge. Beryllium losing the pair of electrons towards fluorine, and hence it gets positive charge. That is why the dipole moment in this BeF bonding is shown in this direction. Okay, so here the vector of this dipole moment is in this direction. Whereas if you see in this bonding, beryllium fluorine bonding, the pair of electrons are pulled towards fluorine in this direction. So the vector is shown in this direction here. So two equal vectors in the opposite direction. Now the resultant dipole moment of this total molecule will be equal to 0, because two vectors are in the opposite direction, the same quantity. The resultant of these two will be null vector, which we call as 0. So we can say this beryllium difluoride is a non-polar molecule. Even though it has polar covalent bonds, the resultant polarity of this molecule is said to be 0. So we can say this as a non-polar molecule with polar covalent bonds. So it is becoming non-polar because of symmetry in the bond arrangement. Both the bonds are in the opposite direction, hence the resultant vector is becoming 0. Okay, let us see some other molecules. In tetra-atomic molecules, for example, BeF3, the dipole moment is 0, although boron fluorine bonds are oriented at an angle of 120 degrees to one another. The three bond moments give a net sum of 0 as the resultant of any 2 is equal to opposite to the third one. So you see here, this molecule also is having symmetry in shape. So the bond polarities are in three directions with 120 angles. The net polarity for this molecule also becomes 0. Hence we can say this molecule also has the molecule with net dipole moment 0, but which has polar covalent bonds. There are polar covalent bonds, but net polarity for this molecule becoming 0, because the sum of these three vectors will become equal to 0. Now let us study an interesting case of NH3 and NF3 molecules. Both the molecules have pyramidal shape with a lone pair of electrons on nitrogen atom. Although fluorine is more electronegative than nitrogen, the resultant dipole moment of NH3 is greater than that of NF3. Why it is, let us see. See, observe once, both the molecules are having similar structure, that is a pyramidal shape, and both are having central atom nitrogen only. But out of these two, the net dipole moment of ammonia molecule is greater than that of net dipole moment of NF3 molecule. Let us see why it is so. This is because in case of NH3, that is ammonia, the orbital dipole moment. So here there is a lone pair of electrons in one orbital on nitrogen, isn't it? There is one lone pair of electrons also. So the dipole moment because of this. So in case of ammonia, the orbital dipole due to lone pair of electrons is in this direction. The dipole moment of NH bonds is in this direction. So all are towards one direction. So the resultant net dipole moment will be in this direction only. So in this ammonia molecule, the orbital dipole due to lone pair is in the same direction as the resultant dipole moment of NH bonds, isn't it? See here, these are the three NH bonds. So it is in this direction, here it is in this direction, dipole moment, here it is in the. If you calculate the vector quantity of these all, the resultant dipole moment will be in this direction. So the dipole because of this orbital also in the same direction. So both are in the same direction. That is why the resultant dipole moment will be greater for this ammonia. Whereas in case of NF3, the orbital dipole moment because of lone pair of electrons is in the opposite direction due to the resultant dipole moment of the 3 NF bonds. So here in the NF bonding, fluorine is more electronegative than nitrogen. That's why now the dipole moment will be in this direction. Whereas in case of NH bonding, nitrogen is more electronegative, so the dipole moment is in this direction. But here out of nitrogen and fluorine, fluorine is being more electronegative, hence the dipole moment will be in this direction. So here it is in this direction. It is in this direction here. Now the resultant of these all three vectors, that is a net dipole moment because of these three bonds is a downward direction. Whereas the dipole moment because of this lone pair of electrons in the orbital is in opposite direction. That is why the resultant dipole moment of this NF3 molecule will be less than that of NH3 molecule. Okay, the orbital dipole because of lone pair decreases the effect of the resultant NF bond moments, which results in the low dipole moment of NF3 as represented here. Okay, in this way it is getting less dipole moment because both are in the opposite directions. The result dipole moment because of these three bonds and the dipole moment of this lone pair of electrons in the orbital, both are in the opposite directions. So this reduces the net dipole moment because of these three, and hence it is having less net dipole moment. Okay, that's about dipole moment. Thank you for watching our video. Please subscribe our YouTube channel AIMS Today for latest updates on recorded videos. Please visit our website aimstoday.in for other information regarding online classes, quizzes, live worksheets, do-it-yourself activities, English classes, and even for coding classes.